When we drop a shirt in a donation bin, we imagine a perfect loop. Old cotton spun directly back into a new garment, keeping the material in constant motion. But the waste stream rarely works like that. According to the European Parliament, roughly 1% of recovered textiles actually make it back into new clothing. This gap has been documented for years. The Ellen MacArthur Foundation highlighted the exact same bottleneck in their analysis of the new textiles economy. While collection bins and sorting plants are necessary, they are downstream from the actual constraint. The fate of these fibers is settled at the start, governed by the technical requirements of the parts they are meant to replace. The non-reusable fraction of recycled fabric follows a very consistent path. It becomes industrial rags, acoustic insulation, and mattress stuffing. These materials end up here because of one specific engineering criteria. They are applications where the material cannot fail because it carries no structural load. We call this downcycling, but that implies the material might eventually move again. In reality, once a fiber is shredded for insulation, it is incredibly difficult to recapture. It has been permanently retired. A circular economy depends less on whether a material can be recycled and more on what it becomes, and whether the assembly is designed to ever let it leave. Every physical product relies on a load path, an invisible internal skeleton that dictates exactly how weight and force move through an object. This animated chart shows the distribution of a material's physical strength. When engineers define the load path, they ignore the typical or average strength in the middle of the curve. They draw a hard limit on the far left side. They design for the bottom of the distribution, ensuring the part survives its worst possible unluckiest instance. The problem is that mechanical recycling violently disrupts that curve. The recovery process shortens cotton fibers and introduces contaminants. The material becomes highly variable depending on the specific grade and sorting equipment used. Designers can work with a material that is consistently weak. They cannot calculate a safety factor for a material whose properties constantly shift. In structural engineering, unpredictable is a disqualifying word. Which brings us back to why recycled clothing becomes mattress stuffing. Nobody computes a structural safety factor for filling. It is the one place where extreme variance genuinely does not matter. There are exceptions, but they require serious intervention. Rutgers University developed a structural composite made from post-consumer plastics, mostly high-density polyethylene and recycled car bumpers. The resulting material is strong enough to carry 120-ton locomotives on U.S. Army railroad bridges. But that capability required a dedicated, expensive blending process and a full structural qualification program. The variants had to be deliberately engineered out of the waste stream. We are seeing new propositions attempt similar leaps with textiles. A recent project by Taylor Leung explores heat-fusing discarded synthetic fabrics into porous structural units, relying entirely on heat rather than adding chemical binders or resins. Because the fibers are bonded thermally instead of chemically, the units can theoretically be melted and refused later. This creates a potential exit strategy, avoiding the permanent dead end of traditional downcycling. Recycled materials do not accidentally walk into the load path. Pushing them up the value chain requires front-loading the cost of variance while the product is still a concept. Upcoming regulations, like the European Union's revised Waste Framework Directive, are actively pushing member states to incorporate more recycled fibers into their manufacturing. But a policy mandate only tells a manufacturer they have to use the material. It cannot answer the geometric question of where those unpredictable fibers actually sit inside the final product's anatomy. That decision is finalized in the very first weeks of a project. When a designer draws a section line, the load path is established. Drawing a rigid skeleton without accommodating material variance forces recycled content into the leftover, non-structural spaces. Escaping the downcycling trap means making a choice about where in your assembly you are willing to accept variance, and making that choice before the initial concept is even completed. Ultimately, utilizing recycled material means finding somewhere it cannot fail. But the designer alone holds the authority to dictate exactly where that threshold of failure lies. Every line drawn early in the process solidifies the physical future of the product. Design decisions are cheap as a sketch, brutal once tooled. See every angle before you build. For more design intelligence, visit deepix.ai.